put it in places there.
Yes, that is the
Figure out the order. Yeah. So, yeah, thanks, and I approve again recording. So my name is Jørgen Villadsen. I'm from the Technical University of Denmark. That's located in the Copenhagen area. For ourselves, the department EuroProofNet. It's the largest mathematics and computer science environment in Denmark. I'm very happy here to present on natural deduction and axioms for propositional and first order logic. I would like to thank my current student Vladimir for helping some of the proofs, and actually some of the proofs you see are like from 2 days ago. We had longer proofs, but now we have better proofs. So first of all, I have a problem because in 10 minutes the happy hour will begin, and since my talk is planned for 1 hour, yeah, I will be alone or kind of miss the.
No, eat everything and drink all of the wine.
But I'm happy you are still here. So I cannot do it in 10 minutes, of course. Maybe if you go out and get wine and come back, that's fine. In the previous talk, some of my work on some other systems, Nadea, and I should also mention CCAM together with Nadea. I just say a few words about it. First of all, I think kind of you should not consider them because it's work done 5 to 10 years ago, and we have better ways to do it now. But we don't have any mistakes currently in the system, so you can go online. They are really available at our web homepage. Simply just type Nadea, compute, DTU, PK, then you are on Nadea and similar for CCAM. But we have better systems, so contact me if you're interested. For Nadea, it means natural deduction assistant. I have an environment in Isabel where basically it's Isabel Hall, but without all the automation. And I think that works a lot better than Nadea. And Nadea it's a web app, and you can only click. That was the old idea. You should not write anything, you click and make a proof. And I showed it like almost 10 years ago when Frederik visited me. You know, Frederik was on some of the other slides. I also mentioned him. And he got very interested and made a very long proof. But we had a longer proof, but he made some hours clicking and made this natural deduction proof. I will show you the formula in a moment. It's not so easy. So I'm happy about that. We can also do it in the same formula in CCAM, but now I will briefly show a better tool for that. By the way, both tools are on logic-tools and GitHub, like you have got the same kind of link for our EuroProofNet. And I should also say this will involve some mathematical and computational linguistics, but mainly it's about proofs. It's about proofs and formal proofs. Everything basically is about formal proofs, and it's also formal proofs about formal proofs. Okay, so we're considering systems of logic, and we use Isabel to verify these systems. So that could be either, for instance, for CCAM, we have a running program you can run, and we verify that proof of a first order logic in Isabel also we verify, and that's what I'm going to consider here. Everything I'm going to show, all the proof systems, they are verified in Isabelle, so we know they are sound and complete. There's simply nothing missing. And also notice the logo for EuroProofNet. It says we have the symbol for validity, so a formula is valid, right? And the logo shows that this must be equivalent to being provable in some proof system, right? This is the logo for EuroProofNet, and this is exactly what you will see and what we have been doing for the last essentially 20 years at least. My group. So here we will have propositional logic, first logic, which will also higher order logic, but I'm not going to show that today. And of course, what we prove here should be valid, but also as again, when it's valid, it should be proven. We also recently found it nice to have languages of arbitrary cardinality. So we have very strong completeness results, also allowing uncountable number of formulas. If you want to have as predicate names, functions over functions over functions of complex numbers, you can have that. Or you can have over real numbers, maybe you like that. Often you are restricted only to natural numbers. And I'm happy with natural numbers, but it's nice to get all these cardinalities done. Okay, so I think that was some words I should say. This is actually a combined Isabelle theory, and we are talking about 6,000 lines in Isabelle. But again, we have better ways, slightly. It's nothing wrong, but we have better ways to do that. Now, yeah, so it's proofs about proofs. I should also say, please ask questions, go along. I really like some interaction. But what I'm going to present, I don't have any, I guess I have some examples, but I don't have really any new results on natural. But as you know, natural deduction, you have only rules. And in axiomatic systems, or what I call axiomatics just for short, we have, of course, axioms, at least one. Otherwise, we cannot start, but we don't have any axioms in the basic natural deduction proof systems. And we also, of course, need at least one rule for building up the axiomatics, right? It's not just enough to specify some axioms. We need, at least even for propositional logic, we need bonus points that will be clear, but also other rules. So I have systems with just a few rules, or with many rules, and some very different kinds of axioms. Okay, so let's go to the next slide. So I have an agenda here with points, including a conclusion. But I discovered I think I need to do a little prelude before going through the outline. So let's do that first. So I really like examples in natural language and doing some reasoning. And I think this is a nice example. It's not my example. It's more than 25 years old. So it says if every person that is not rich has a rich father, then some rich person must have a rich grandfather. So this is what I call the grandfather formula, right? And that it's mentioned first time on this page, on 28 in this handbook of tableau method. It's a big book, but it's not. I mean, the proof is kind of discussed, not in full. On many pages. It's like the running example, but they don't show the whole proof, but they talk about it and on I think more than 20 pages. So and of course we have it in these systems, and it's a standard for our students to try to study. This is in the syntax of the textbook we use, you would like to have a function for father and a predicate for being rich, just of one argument, and also the function takes an individual to person's father. In Isabelle, we do everything in Isabelle just to get used to the syntax. You have functions applied to an argument, you write it this way, not like that. So you skip some parentheses, but then again, you need to group that together to. So these things are special quotes in Isabelle, so you can. They're essentially just quotes, meaning that we want to have this proposition and then to put up the quotes, and then here this is easily. I mean, it takes less than 1 millisecond to prove it for Isabelle. You can just use auto instead of write by auto. But auto is actually calling something a tableau prover, by the way, called BLAST. And BLAST is probably a better way to do it. Because this is pure logic. So, and auto will do many things. You can also use resolution-based provers like Mason and Villadsen, which show later. So you can see, if I want to give this problem to students, I would like to maybe disable all the automation, and they have to do it by. I think this is a good example. It's definitely not trivial, I would say. And if you know any larger, I mean, there are, of course, larger things to formalize, but still something you can easily understand the problem, please let me know. But this is like one of our main problems. So now you know about that. Why do I think Isabelle is relevant here? So I was not exactly sure how much Isabelle we would have. We have actually quite a lot of applications with Isabelle. First of all, Isabelle is 40 years old now. The first version was made publicly available and still download it and try it out. Of course, it's very small, but this was the year after. So I think the celebration for 40 years will be next year, but the paper about it by Larry Paulson was in 85. That's for sure. It came out back then. So it's an old system. It's also the only system of this kind with possibility for doing math, where it's actually born as a baby. It has no logic. So you start, it's called pure. So it cannot show anything. It has no language, so to speak, but it knows how to define natural deduction proof systems, but it comes with nothing. But most people will use the higher order logic, but you have also set theory and type theory in Isabelle, but normally it's just higher order logic. There's a new project. Yeah, it's been around for some months, but so they're not very far, but they are considering people to work in 6 proof systems and try to formalize all the proofs. So I have 2 examples here. I already talked about completeness proof, and you have incompleteness, formal proofs of the completeness theorem and the incompleteness theorem of theorems. And we want to do that in proof systems. And they are currently only considering 6. So there are, of course, other like ACTA and many other systems, but these are the ones, and these are the ones you see down here. So that's a new project. It's called Formalizing 1000+ Theorems, and they only use the Wikipedia. They must have a Wikipedia page for people to see by this project. There was, for years, maybe you know, these 100 theorems, and the current list of these theorems, they have all been formalized in at least one proof system, except the Maslach theorem, and there's of course a project by because I've been working on that for some years still. But This is the current count, and you can see higher logic is doing very well. The type theory, dependent types systems are also in the top, and I think this will not grow so much. It's difficult to get maybe more results in these because the remaining problems are very hard. So I think also this shows, yeah, Isabel is doing very well. The good thing about Isabel Hall is that it's very easy to explain what it's about. It's high order logic, and as I said, Isabel comes with this pure, so you import pure, and then it knows nothing, and then you have these 7 natural deduction rules. So you write them exactly as written here with everything. There are some special symbols, so you write them, and then you have full higher order logic and can define anything. They are classical higher order logic only from these 7 axioms. It's not something you have to look for them in the Isabel system, but these are exactly the ones. Isabel has 2 notations. So for defining the natural, maybe you know all these, but I like to repeat. So it has two things to formalize the natural deduction rules. One is this double arrow, and another one is this big and symbol. It's a big and symbol, and it works like a quantifier. Okay. So these are the only 2 things Isabel knows about, and the arrow here is for the basic working of the natural deduction rules, and it associates as usual for arrows to the right. So you have like here the parentheses here. Because you have multiple here, so it's the only way you have to use it. So this is similar to exponent. You have an implication, and from that you get something that if you also have P, which has to match that one, of course you get Q. So this is the implication elimination rule. You postulate that, and then Isabel knows more than it knew before because it didn't have any rules before that. And how do you formalize the implication introduction? Well, you want to introduce the implication, so you assume the P, and then you simply use the same arrow here. So you can use the arrow to branch the proof, right? So you have these 2, and you work backwards from this one, you get these 2 subgoals. This is your goal. So the normal rule, you can also have multiple branches if you like. But here you add a local assumption. It's only going to be used for the proof of Q. So the double implication called meta implication is doing the work of several things. Then for the inversion quantifier, we introduce that with this rule. So if we have the scope for the quantifier is only here. This is the formula. And it's exactly how you write it in Isabel, and then you can choose P of C. And C it looks like a constant that you apply to this predicate, but it's not. It's any term. So I could write T. Sometimes I write T also to signal it's any term. And you can have functions in the term, and you can have functions with any kind of arguments. We only saw grandfather with one argument, you can have any kind. So even if you write this, Isabel will allow you to have any arguments, also for the predicate P. P is not necessarily only one argument. It just means that it has many arguments. Maybe it could be also a whole formula, and C is syntactic inside. So substitution is built in. And so this is the elimination rule. We can instantiate specialization of the universal statement. You can also introduce the quantifier, and there you have to say that it has to be for an arbitrary argument here. I wrote X here, but the binding is local here, so you could write C if you like, or you could write T, or you could use Y. Doesn't matter what you write, it's here. So, but it's like you use X over here. Why not use X here? They are independent. So that's giving you all the logic you need, and you define all the logical operators, false, true, conjunction, disjunction. When you come to implication, it's normal that you use a Leibniz definition for that. We use definitions for all the operators, where some two things are equal if they have the same properties. And that we use that for equality. And Isabel will never show a biimplication. You can write a biimplication, but whatever Isabel shows you, it will always use equality for the biimplication. So why not write it? This is biimplication, but you can write it, but it will be always shown. And you need that you need this particular introduction. We'll start to follow from that one. So you need to add that. I think even constructive people are kind of happy with it, although this will give you only intuitionistic logic. But I think constructive people are happy if you from P can get Q, and from Q can get P that considered equal by extensionality. But the real extensionality action comes from the two functions f and g, and if they have the same argument, the same result for all arguments, then they are equal. You add that extensionality. So, unlike in computer science, our functions or algorithms here, they take no time and use no resources, memory or anything. So they are equal. Doesn't matter if it's bubble sort or quick sort, it's the same. And then you add, if you like, but now we are moving definitely beyond intuitionistic logic. Maybe they will accept extensionality in some cases, but choice will give you classical logic. So it will give you law of scrutiny. And in my course, I always derive that it does take more than 50 lines to do it, but it's a nice proof that once you have this kind of global choice, so you have some P is not empty, there's something being a P, then epsilon, Hilbert's epsilon, simple essentially, will choose, take a predicate, we are talking higher order logic here, so it takes the predicate P that you have from here, and it will choose one of them. Maybe there are more than one, but at least one, and that will have the property P. And that gives you classical logic. You simply only have two true values, true and false. Yeah, so that's Isabel. You didn't know. Any questions? Yeah. Yeah. So that takes about 10 pages to do the whole development without the automation. So of course, Isabel has billions of lines, but that's for the automation part. Okay, and by the way, let's just these elimination introduction rules, you're never going to use them directly by name. It's much better so that Isabel do it directly. So you don't really have to think much about the naming. Extinction and choice, there you have to think about it. And you have to write usually that you have to use it. So one thing that now we're moving from the higher order logic to a very small part of logic, right? Even smaller than propositional logic, just implicational. So that's, I'm going to talk quite a bit about that, because that's where the Axioms starts really. So implicational logic, it's higher order logic, but only with implication. So it's first order logic only with implication. So it's propositional logic only implication. There's only implication. There's no falsity, no negation, no conjunction, no disjunction. Still, there's a difference between intuitionistic logic and classical logic. First law is one example that doesn't hold in intuitionistic logic. So I don't want to go into all the details. I have used this recently in teaching, and Tedu is theory improving components for educational software. So I did talk a bit about that there, but there's currently no paper on the topic. But I think these rules are interesting, and there's only one axiom, so that's the minimum you need to get going. The interesting idea is that normally when you think of, if you know Peirce law, you think of, okay, that's what I add to intuitionistic logic or law of double negation to get classical logic. But that's actually not true. There are much weaker systems, and if you add Peirce law to any of those, you get classical logic. So it's not clear that intuitionistic logic is the correct stepping stone. Okay, so and these logics, for example, are called PCI and PCK logics. So this was primarily more than 50 years ago. The PCI and PCK stands for some combinators by Schoenfinkel, exactly in, plus minus 1 year, 100 years ago. 1924. So that's what they stand for, but the I is like P implies P. This is the idea. And this is transitivity, and I'm going to talk a lot about that. So the way I explain it is that you really want to prove the P. Q is kind of a guard, so this is an assumption. You have that, and for that assumption, you find some lemma, so to speak, but not really a normal lemma that you can prove from Q, and that is sufficient to prove P. Right? So you have to work backwards, even if you are working in a schematic system. Notice here, we don't have any, this is not natural deduction. We don't have any assumptions. Natural deduction, as you saw on the last slide, we have had 7 rules and no axioms at all. None of the rules were axioms, because there are at least assumptions that you saw from implication introduction. Right? But here, everything you have the axioms and you have your rule, but it's all very direct. You have bonus ponens, and I have bonus ponens here. This looks the same as before, but notice none of the other ones will add any assumptions. So we stay because there's not this nesting of that. Okay, so this is a very basic one. So it's very similar to P implies P, but as a rule. So here it goes Q to Q. So if you want to prove P, you can prove P, and you're allowed to add Q to Q for any Q. Okay. I think it's nice, and then you can have instead of Peirce law, you have Peirce rule, where the thing you are going to add is a contradiction. You say P implies anything, and that's, we have only implication logic, so you don't have falsity. So saying not P means that P implies anything, because the worst case is that Q is false, and that's meaning negation then, essentially. So you see, these are very similar rules, and inspired by what you did in natural deduction, also this one, of course, of natural deduction. And then I already explained the axiom, but then one thing we usually want to start with to explain is that, okay, you want to prove P, and you have some assumptions, Q and also R, but you can swap them, right? So it's fine if you swap them. So commutativity, that's the C. It's a commutativity rule. So this one allows you to do that, or if you want to show that, you have to show that instead. And then there's also a deletion rule where you still want to have two assumptions, but maybe you don't really need the R, and that goes away by here. So they're very similar, you know, right? And this is all you need, and you get classical logic for implicational fragment, what I call implicational logic. But the interesting thing is that what happens if we take away this the first rule, right? We don't get intrinsic logic. We get something much weaker, namely the BCK logic. I'll explain a bit more later, but essentially BCK logic is where you can only use an assumption once. And the BCI logic is, the BCI logic is at most once. And BCI logic is you have to use only once, and you have to use it. Because take just the two lines up here, CR, IR, here. Forget about the one. This one meant that we get to classical logic, but also with this one. What can you do? You have a basic property of lemma, postponement. You can compute your assumptions, and you can introduce identity. Right? You only have these four things. That's BCI. You are not allowed to delete an assumption. For that, you need the DR. The names here are maybe not the best one, but these are totally historically correct. So here you can see having the opportunity to not if you don't have this rule, you have to use it, right? And you can. It's possible also to take this one away, but then you are in a linear setting where also the ordering of the axioms or the assumptions matters, and we don't want that. I think we are fine that the ordering matters, but I guess students, they are happy with, why the ordering doesn't matter of my assumptions. I don't want to have the opportunity to delete anything, because why have an assumption you don't use? Why not make your proof such that you don't introduce assumptions you don't use? Makes sense, I think. And also, maybe you want to use an assumption many times, but only a finite number, of course, in your finite proof. So maybe you work in a setting where you what did I say? You only want to you want to use it once, and you must use it, right? So don't introduce anything you don't need, and if you want to use it many times, then add it as an assumption many times in your proof. So your proof will get longer, but then more explicit. You can see all uses. So I think this is it's nice, and we have shown so this proof system you have here with just one axiom and 5 rules. We have shown that this is complete, and the only thing is that we don't actually have a real. We have a proof in Isabel, and it doesn't take more like a second for the whole proof. But Isabel does not give us the details, so we don't have a proof that will satisfy Shevich or other logicians not trusting Isabel, right? Because Isabel works for some milliseconds, and it finds all the steps, all the proofs from this one, but I don't have basic proofs that you can write down on a page for this one yet, but we are getting close. Okay, so this now you know something about that. Okay, my recent papers relevant. For instance, last year at the Tedu, I talked about our improvements of the sequence verifier, which we call now mini-calc, minimal signal calculus. And we also had the theory in the Journal of Logical Computation. So how are we doing that? Completeness. It actually also has tableaus and natural deduction, even though it doesn't say it all the time. Teaching higher logic, that's something like the 7 axioms, the 7 rules I talked about. See it? And then we have some work on holding proof body, where you on a web page do interactive proof, so you don't have to install Isabelle. Isabelle is very easy to install. It's just one click. But the good thing about having it on the web is that if the students allow, you can monitor whatever they do. All the clicks, all the movements, all the timing, where do they think for half a minute. We monitor that and can provide better learning to them interactively. So this is the idea. So these are some of the systems. Okay, so for 20 years I've used this book in the earlier versions and also the first edition. I think it really is a good standard textbook for mathematical, but nobody wants to read all 300 pages to understand. The main systems they are tableaus and resolution. These are the main systems for first order logic. So the idea for the last 20 years has been to do everything in this book, also resolution. I'm not going to talk about that. But for all the systems and also for natural deduction, doing it in Isabelle, so we know what. This is the LaTeX, and it improves completeness for first order logic, but it's making a lot of big steps and so on. So now we have it in Isabelle. Basically, we have the whole book in Isabelle. So this is just to show you how it looks. This minimal signal. The minimal is because when you see the list of rules for signal calculus here, it's much more minimal than you expect. So there's really no fat or anything. It's very minimal. It also works on list. It doesn't have 2 sides. That normal signal calculus have 2 sides. It's on one side. We do have right groups and left groups. So this is just an example. It's not the grandfather. It's a simpler formula, but still, you can see it has implications. So of course, you're going to use on right group for implications. You're then going to, among your assumptions, to instantiate the universal quantifier with the A, and then you're going to get the P out here that you can get over here also, and the Q of A from there, and you have to commute. So you can see the rules are like that, and then there's something extra because we need to optimize, and these are all list of disjunctions. So in order to prove this formula, I need to explain in details, but the thing is that you have to either the left-hand side is not the case or the right-hand side can be proved. So the notation is using the Browning indices, so variables have numbers. Students, they are very happy about it. It's all ASCII. We can have a competition who can prove the formula the quickest, and Isabelle checks everything. And they can hand in using Isabelle files. But they have this web app where they have an editor, nice one with folding and so on, so you can fold subgroup. And here's your branching, so the thing branches, of course. And you just have to get used to, instead of writing negation of Q of A, you write it in like that. And then you copy paste things from when you move along as you break up. So the second proof is like opposite down. I'm not going to talk about this mini-calc, but I know of no faster way to prove many of the formulas. And this grandfather, they will have to hand in that proof. Of course, that will involve not only 5 applications of the rules, but I think maybe 40. So I don't know. You can also make better or worse proofs. So the system will, of course, display the normal negation of conjunction, disjunction operators for you. But it actually works amazingly just having this text format that you are so good on. So no clicking here, you write that, and this is plain text. And then you have the support and Isabel for Propositional. And the system is sound and complete, so we know they can prove it from these very simple. Okay, that's not what it's about. But now we cover still some ground. So what I'm going to talk about? So I'm going to consider natural deduction. Then when we have to start using axioms, we have to start with the basics. So E plus P. Let's see that on paper and Isabel. I want to discuss how to move from propositional to unification logic. I want to show you exactly how I do soundness and completeness for unification logic, because since you don't have negation around you, you have to use very combinatory arguments. So you cannot, if you think, normally when we do first of all logic and want to have a proof for propositional logic, it's just basically to take the proof, a couple of thousand lines in Isabel for first order logic, erase the quantifiers in first order logic, and then erase everything not used, and then you have completeness for the propositional part. But it doesn't work when you don't have negation, because then you do kind of this maximum consistent sets, consistency properties and so on. It doesn't really work. So you have to do it in a more direct way. But that's fun also. Then we move to first order logic and axiomatics and more about this BCD logic, which is new. And then I have all particular systems I want to sell to you. And we know there are some. So that's the agenda. So now let's move to the thing. So I asked Vladimir to prove it, and he wanted to use law of excluded middle, so here is a standard proof with Isabel about it. It's based on a version. That's how I introduce it. So normally you think law of excluded middle is like a good starting point for making classical proofs. But actually this version of, it's yet another version of Birch's law, because it has the assumptions here. So it's a natural deduction rule. You prove P by adding this thing as an assumption in the proof of P, right? So you can prove anything by assuming a contradiction, assuming this and showing the contradiction in your proof of P. So let's see how it goes. So this is just to remind me, this is basic classic logic, but then a little intuitionistic logic to show that formula. The longer proof is like these picture lines, so I don't want to show that. So I have a basic proof of from the choice action, or choice rule. But law of excluded middle, how do you prove that? Well, you use that thing up here, because you have a disjunction here, you cannot do much. And Isabel will allow you to instantiate the view with, so this is first order logic. So you instantiate what you have as an assumption, is where you also have Q as falsity, right? So we now make that assumption and go on to show the P, the whole thing that we started out with. And then the student needs some idea. Maybe the student could prove the negation of P, and that's a subproof. And of course, from the negation of P, you can show just adding P to my disjunction. Yeah, then you're done. So we show that by assuming P, and again, we do that and get to falsity here. So that's the definition of negation, is that P implies falsity, and that allows you to assume the P and show falsity. And from P we can add the disjunction part, and with that and the assumption we have, we get that. So it all works very nice. I hope I got it kind of right. So this is just a warm-up exercise to do the whole. And I have shown this, and I normally would not like to use lawful student middle, but directly in simple. But this is what the student came up with. I blanked out all these secret things because I don't want the solution on the web. But if you know something about Isabel, you know what you assume up here. The assume up here, this is of course the left-hand side here. And what you have to show down here is the right-hand side. But this is the whole proof. What is missing are a number of formulas, right? So it's all going to be more or less sub-formulas of what you have already. So it's a bit more messy, but you see some structure, and there are some child and father and grandfather introduced, and you have the structure and introduction. So as I said, it can be shortened a bit, but not much, and you need, of course, to have all the parts to have the thing. So I think this is good for natural code. Okay, so that was that part. Now let's move to the axioms. And in the textbook that we use, there's a lot of parentheses not needed, and there are these 3 axioms, and it's all based on negation. But we only consider axioms 1 and 2 for logic. And then there's basically only one proof directly in the book, the textbook, saying that, yeah, if you instantiate axiom 2 with C being A to A and B and so on, you have to instantiate it in the right way, and you have to instantiate axiom 2 here with Q over being this thing. You have to make another instantiation down here, you use more components, you get it, right? So we know that. This is in the book. Then what should we do in Isabel? First of all, we of course, we don't want A and B, and we don't want all the parentheses. So this is axiom 1, and this is axiom 2 in Isabel. And in Isabel, we would give it a name. So it's actually the S combinator and the K combinator. And of course, these are straightforward to prove. And here is the same proof as the slide before, exactly the same, just with less parentheses and only P appears. And so you have axiom 2, which is S, and I call that one K. And as you know, I combinator is SKK. I don't know if you know that. So, and now in Isabel, all the instantiations to like the things you have to instantiate here, Isabel will do that by unification. So you just say I use monosponents twice and the S and K. And basically the monosponents and the S and the K will be evaluated first because monosponents takes 2 arguments. And the result here will be just another monosponents of K. It's the same structure, and you just write the whole, there's no automation. The whole proof is single dot in Isabel, meaning it's in front of you. It's just using what it already had. So that's one observation, that Isabel actually works very well with axioms. You don't have to write all this up. You can write the proof as a line like that. So it works nice. Now, propositional logical implication lot. There's a nice elements book, but it's not geometry. Elements of mathematical logic. It came out 2nd edition in English, but it's work by Siewicz, but Pressburger made the notes in the 20s, and he somehow found out, I don't know how, it takes more than 100 pages and I believe almost 200 theorems. He established that this system is, of course, sound. That's not a problem, but it's also for propositional logic. It's simply amazing. It's so short. You have the transitivity, and then you have two rules with negation. One is exactly a version of Peirce's law, but not with the P applies Q, but the negation of P. And then you have explosion here. Q and not Q gives you anything, any P. Amazing. You could show completeness for that one. The problem is that if we take away negation, because we want to consider implicational logic, this formula alone is not a single axiom for implicational logic. So what should we fill in instead? Because we want to do implicational logic, and we cannot use the axioms with negation. They work when you have negation and as a primitive, not defined, but because if it's defined, it simply is not needed. So if you have this definition, this will not go through. But if it's primitive, fine. Now we don't want it. So Tarski and improved by Bernay, they came up with this system. So it's the same transitivity, but there's a simple one called the K axiom here, and then Peirce's law. So that's that works, and we, like 3-4 years ago, we formalized the proof on Wikipedia for that, and I'm going to show you some parts of that. So this is complete for implicational logic, classical logic. On the Wikipedia page it says Bernay Tarski also, I mean, maybe in alphabetical order, but who is really responsible for this one? Because this is Peirce's law, right? And this one is from Frege, and this one is Vukocevic. So, but they put it together. Bernay was essentially to get it down to transitivity, but yeah, these are the persons in the 20s doing this. So now, how do we do it? This is exactly how it looks in Isabel, and there's nothing left out here. You start by defining the formulas. We want any kind of formulas. So we have propositional simple. We have a type variable here. This is the quote A notation here, and we actually use this currency symbol, this sun symbol. It's not shown on any on the things here, but we use that as transferring whatever kind of thing we have. If you have complex numbers or functions or whatever, as your propositional symbols, we transfer it into a formula, atomic formula, and then you have implication. Just have it in fixed, right? And then semantics. Well, if you have, as I said, these propositional symbols, you just look it up in interpretation. You don't have to write anything else. Isabel will infer the types of your interpretation, which is a function from your names to the true values. You simply use the long arrow, which is Isabel implication, for giving the semantics of the small arrow, which is my implicational logic. And then you state inductively with the only rule being monoponents at the axioms, K, P, and T for transitivity, Peirce's law, and the K combinator. Completely automatically, this is also like standard thing you induct on the formula. So anything you can prove for any interpretation, it will be true. So that's completely automatic. And then you have only these, and how are you going to combine them? We saw how you get the I formula, right? P to P. But how are you going to get essentially the S combinator? That's the hard thing, to get this from Frege. Because that one, the first one, gives you fusionistic logic. And this one will work, but only if you have already shown that you can compute P and Q in here. So change the ordering of assumptions. And that one will work. Yeah, and these are some of the things we used a Python program for some hours to find it. But the thing is that we had a longer proof, but where all the steps were by Isabel using Betis and Mason. So, but it's simply very nice that you have the proof, because this you can write up. It takes like a page or two, but it's just applications of bonus moments on the basic stuff, right? And of course we have, as you saw, one dot proof, which is all by Axioms, as we saw before, but now it's not in Isabel Hall, but now it's in this calculus, so that's why we use the uppercase today. So it all works out, and skipping some lines. If I get the next slide. I think it also goes in. Yeah. We get the soundness in Isabel, that's in EuroProofNet, that if you show a formula, then it's valid for all interpretation. Completeness, you need an explicit quantifier, because this one is universally quantified as a conclusion, but you want to make sure that it's valid for all, or true for all interpretations, and then you must be able to find the proof. This one takes 100 lines. You saw some of the lines before. It takes only 1 second to process it, and then of course combining these two trivially gives you that is equivalent to being valid, right? We could even go for one proof with this putting all together. These are from the basic ones, only AT, AP, and AP. We found this proof. I'm sure nobody can do that without using some tools like Python we used, and some things in Isabel. Okay, so now you have an idea of what is that, but we really want to get to first of all. This was just explanation of the things. If you look up in a standard text, I refer to, you can take other. You have, of course, the propositional formulas, and then some axioms, and also kind of generalization rule that you can generalize here for arbitrary A, for the universal quantifier exponent, and you need to somehow make it work with implication. And you see there, okay, this is not surprising. ABC must be your first order formulas. But you need some free variables here, and this is a form of free variable, and this is not free of the formula, and very complicated descriptions of what it means. So this is not very good axiomatic system. So what can we do instead? So here is one system exactly with these things. So this will come later, but these are the B, C, D, and this is one exponent. This is the I rule and the P rule for burst, and you have explosion. If you, for some assumptions, Q can get false, then anything holds, any P holds, and you can instantiate. This is how you normally write that in Isabel, now with the T, and these are not natural, these are axiomatics. There are no assumptions here, but still you have to kind of mimic the assumptions here. So for the universal quantifier and also for the instantiation here, you have some kind of assumptions on the left hand side of implication, and there's no restriction here, but here's the restriction that what you have here for X must be fresh in, not appear in Q and P prime. P prime is because P up here is a propositional formula, and here it's a predicate. So this is exactly how you can do it in Isabel notation. And this is the one that P result. I call it BCD. It's my pin logic. So this has much fewer assumptions than it doesn't overload all the notation. It doesn't have all the side conditions, and it scales in the way that if you just take this part, you have BCI and you have BCK logics and you have full first order logic with false. You get classical logic and you get first order logic. So you have all these systems nicely structured, where what you have here on the previous textbook, it's fine, but it's a mess really. So just a few words more on the BCI logic. So again, the combinators, when you write these combinators, you saw it earlier as a group, but as a combinator, this is all implications. The same you need now. Some parentheses here. The K action is this thing, and the I is that. Taking the BC and the I get you BCI logic. Instead of I take K, you get BCK, but it's the same as taking I together with BCD. So you see the D thing here is actually an instantiation of that thing over here. You rename the Q to R, and you rename the P to Q to P, the UP. So it's an extension of that. So it all works nicely, and these logics, both of them, are weaker than intuitionistic or false classical logic. So again, you're only allowed to use assumptions of most ones, and in the BCI you have to use it. You cannot omit use. So my suggestion is, instead of you have monosponents, that's fine, and you have generalization. Here you can introduce the universal quantifier, and you have these nice axioms from Banitarsky. These are longer, but I think it's very nice to get more rules and have exactly these axioms that you can talk about. We are not replacing these two things, but the 5 up here we're replacing with these 3 other axioms and these rules. I think it's easier to explain what's doing. This is very arbitrary what you have up here, the collection. So much better for understanding what's going on, and you have these nice subsystems. Putting it all together. So what I showed when I show it here, this is using Isabelle notation. So I only get soundness here because you cannot see, but this has been done in Isabelle. So this is sound. Isabelle, of course, has first order logic as a part. And you have this notation, right? But if you want to have it as a data type and show completeness, Isabelle cannot show its own completeness. It cannot inspect its own rules. So we need to make a deep embedding, like you saw from the from the applicational logic. So we need to formalize the turnstile as the deduction definition. And we need to have some kind of program, I call it, that simply checks whether this function or constant A is in that formula. So it's just going through the formula. Did I find it? Did I not find it? It's very simple program, the new. And substitution, you have to do that with the point indices. It's quite simple, not trivial. So we have to take care of all the substitution. Luckily, we can get nice notation, and we don't need to mention what variable, because this is always the one next 0 in the point indices. So this, I know these rules are complete. The ones I showed before are new only soundness, but here it's the same rules, but written in a completely direct way. Also have to explain this star, but this will take any function and of one argument, of no 0 arguments, and make it into a constant, because constants are functions with no arguments. So this is how we do it. So it's all precisely defined, and this one is based on the BCI logic, BCD logic, and then we have that one. I have it also. This is with one simple turnstile, but then it's possible also to have like a double turnstile. It's not the validity. You see the line is in front here, and I think this is nice to have it in the same file and this is quite easy to show completeness of that based on the other one. So it's really nice. It's much more difficult to work with this thing and show it, but the actions I had on the slide before, BCD, it's so slow, the BCD, these are actually working very well in practice. So it's just 50 lines or less to show that this system is equivalent. Of course, this has the 5 axioms and the 2 rules, as you expect. And then I just have some alternative ones I like very much. So first of all, it is possible to have a system with 4 axioms and have double negation. But remember, double negation is P implies falsity. So it's not a positive, but you can write it like abbreviation like this. And this system, this has X, S, and K as the active. So here you have intuition. This is sound and complete also. And of course, and then I kind of like a particular one where you only have one axiom, and that's the transitivity, and then everything else are the you saw that earlier. Also, this is the most novel thing. So you have all the rules, and then this is the variant. It's really very natural deduction-like. You cannot have full natural deduction because that's only natural deduction. But it has a lot of the same thing. You want to show P under some assumptions. What can you do? It's different. It's not natural deduction, but it has some of the same flavor. Okay, I don't know what the time is, but happy hour probably long gone. For the conclusions, just very briefly, we have used it for many years to teach meta theory of propositional first order logic, but the last 5 years since I've done resolution, natural deduction, chicken calculus, I haven't talked about resolution. That's complicated. We also do superposition, and at least order resolution, but it's so complicated. But axiomatic systems have grown on me. I mean, it's possible to work with it in Isabel. You can use automation, and you can have students to prove actual stuff, not the grandfather, but other stuff, and they can study the soundness and completeness. They can study soundness and completeness of implicational logic, own implication, and it's just less than 200 lines. But for the big ones, it takes 2,000 lines for getting these basic systems. But then you know things right. And any kind of is supported. Yeah. So we looked at, I guess, altogether maybe 100 different axiom systems. There is a whole zoo of axioms, right? But these are, I think, are the main interesting ones. You can have very many. You have one where all the axioms at most have 5 implications, and some of the ones we have had more, but then you can do it differently, and you can have so many different axioms. But I think these are nice because they link to natural deduction. I'm done now. Thanks.
Thank you very much. Questions? Answers? Yes, welcome.
So, thank you for the talk. How did you prove the or what was the proof of completeness for classical first order logic? Can you show it, please?
Okay, I didn't show it directly, so it looks like that. Where the P is that, but this doesn't work for. I mean, you have to do some modifications because you actually prove a stronger result where you consider for the completeness particular term models, right? So that will show, and for the proof also you need actually, since we don't even assume that we have an infinite supply of constants, so we actually need that's at least sufficient to have infinite number of functions because we use them to instantiate, right? And we also need to have at least as many function symbols as we have predicates in cardinality. So there are some assumptions, but if you work like with natural numbers for the symbols, it all goes away. But still, the completeness is restricted to particular subset of soundness for all, but some completeness. So you can still use this symbol, but it has a different meaning for completeness. Yeah, true. So yeah.
So it was a long proof with like a lot of construction. It was not just like you just wrote auto and
No, and I didn't mention. I make sure of that in the paper. It's done with, in particular, Asta Halkær. It used to be from. It's in the Arca form proof. She did a lot of work, and we have. I mean, she did it as my PhD student, and we have absorbed many of these results here. So we didn't start from scratch. We had proofs of that deduction calculus, and honestly, we worked on a solution. So that's the nice thing. It's based on things in the Arca form proofs, but not the actual files you need to get from me. But I'll make them available. Yeah. Yeah. Good question. Yeah, thanks.
Some more questions? Jørgen, thank you very much.
Yeah, and I of course available. And now I also used 1 hour and 10 minutes. So happy hour is all gone.
But we can nevertheless see, maybe still there is something.
There's something. Thanks for.
So thank you for the day. See you.
Thanks.
Thank you. Let's stop very forward.